So, good morning. Thank you for coming the day after the test. So these are the results here, the distribution of score. As you know, this will be a normal 90, 80, 70 break to the grade. Well, it's a normal distribution. If will be just this, probably will lower the break of the grade, so will be something like this, maybe. We didn't put the number, we don't know. And those of you that get over 90, again, you'll be happy. We'll have an A anyway. B the same is clearly. We are not sure about this breakout, but you have extra points by showing up in the class. We'll give you a quiz today, maybe next time. Or you have also that source to sync assignment that will give you extra points. So all of the scores will eventually move a bit up because of this extra points you work on. But those of you that are down with the scores into the 60s, again, this was just one of the 4 tests. So things are moving, so you have to try to do better next time. And do the extra assignments and show up in the class. The scores will go up. I'm sure about that. So there are some, I usually check the questions. So there are some questions that were not very well answered. And the question then is because I didn't explain it correctly or because you didn't understood, there was a mistake. And one of the question was this, like what are these sedimentary structures? Anyone remember what they are? Cross strata. So this was actually a well answered question. But then was the other one was about which direction the paleo flow was going. Any try of the answer? Yes, but you'll be surprised less than half put something else. So, you know, again, these are, if you think about the ripple or a dune, see the Stoss and Lee side, they migrate and you preserve just the forceps of the Lee side. And then it's next and next and next. That's why they don't preserve the whole form, like bed form, but just the forceps or the Lee side. So remember about this. It's important for you to know. You can practice this when you walk around the campus. There are some building stones that they have this kind of structures. So another one was this, which I thought is important for you as engineers. What is the maximum porosity associated with the well-sorted sand? You know, the maximum at the very surface before you start compacting, before you do anything to it. What, can you guess the number there? Say it. It's about 50. Actually, it's less than 50. Some people report more. And in some of the slides I was showing you was a graph like this. They didn't quite take it to the surface here. They're still a few hundred meters deep, but it's coming close to 40. Okay? And then was another table we discussed porosity. In some experiments, well-sorted sand was getting to 42, 43%. In the theory, I think they say if they're perfectly round, you can get up to 47%. So just to know, you know, this kind of porosity maximum of sand if it's a loose sand. Another one here, what was the 3 grain sizes classes used for plastic rock classification? Can you guess a number or answer there? C? Well, that's what I had in mind when I had D in oh no, what is that? Mud, sandstone. Well, I had this one in mind, but then was wrong because we discussed about sand-silt clay classification. So I think this was a yield pose question. So those of you that put clay or C, like you say, or clay, sand, silt, that will be a correct answer. So we'll change that. Okay. So this was a poorly asked question. I had in mind mud, sand, and gravel because it's taking all classes of the sciences. But again, we discussed about fine rocks. We discussed just, clay, silt, and sand as another classification for fine rocks. Questions about these things? Yes?
If it would have been mudstone, sandstone, and conglomerate, would that have been an answer?
No, because they're stones, Anyway, so it was just a kind of wrong on my side to put all of these answers, which they kind of overlap and they're different classifications. So I had in mind D again, but according to some of the classes we discussed, but at the same time, soil scientists, the USGS, they use more of this thing. So it just was a trouble question to ask. Again, keep in mind, it's preferred to have the gravel because it's including the conglomerates as rocks rather than just finer. Questions about this? So I went fast over that because we have some important topics. So the second part, on the second quarter, what we call it, of the lectures will be on something we call depositional systems. And we talk plastic first, so glass particles, because that is all of the first half of the class. In the second half, we'll talk more about carbonate rocks, limestone. And today, what we will discuss as a part of depositional systems, on this diagram you have everything from higher relief mountains to the deepest part of the basin. We break these environments in different types. And today we'll discuss about the fan systems, what's closer to the mountains. We'll also discuss about aeolian or wind systems. And we'll see how much time we have to get into the lake systems. It's quite a lot, but we have to cover all of this in a few lectures. There are books written about just one of these systems, like aeolian, for example. If you go into great depth, we don't have time, and for your interest, again, as maybe petroleum engineers, you don't have to know quite all the details. But why do we care about this? Excuse me. Oh, you didn't tell me to turn the microphone on. All of this straight. You turn it on. So why study deposition systems? Well, we want to understand kind of the source to sink, like you have the exercise of the sedimental dispersal. So as the sediments are weathered and then eroded and transported away from the source, that will be the higher relief. They will go through the rivers, and then eventually we reach deltas that form at the edges of the land, okay, close to the shorelines. And then some of the sediments will be transported onto the shelves and eventually into deep water. So we have to make a difference between these things because within each system, the sediment will have different properties. So you will have different grain sizes, if we discuss about that, or we have different geometry of the bodies, the sand bodies that we eventually will look for. And the second thing is that we can predict. So if you go into oil and gas, again, I hope most of you will go, well, you have just discrete observation points. One well or some seismic in one location, and you will be asked to predict what's happening outside of where you have the data. So a good understanding of these systems then allow you to predict if I have a river here, downstream somewhere will be a delta. And what will be downstream of a delta is not a stream anymore. What do you expect? Yeah, so it will be some marine environments. Also, if you know what environment you are, you know how to predict your, let's say, sun body geometries. So we'll get over some of these observations. Again, here it's a messy slide with a lot of data, but this is you might have to work with. Again, to convince you to pay attention of this depositional systems, is that here it's a map with the Wyoming Basin, Wind River Basin, and zooming into that area, I show you the dots where the dots represent wells on the map. So that's what you have as data in the subsurface. And the question is, well, where your reservoir is. If you look at the scale here, this is like 10 kilometers. So these are kilometers apart wells. Okay. So remember how large is the reservoir you're looking for? Meters, maybe tens of meters, and kilometers, maybe in length. So you have to make the most you can from the data. And the data here usually is coming well logs like you have on the lower right here, will be some physical properties of the rocks. You don't really see the rocks. Okay. You learn, if you didn't take classes, you'll learn about this, gamma ray, that's radioactivity, properties of the rocks. You have porosity through neutron porosity, electrical properties of the rocks. And you'll make sense, is it sand, mud, or what type of rocks you might have. But you don't see channels, you don't see the rocks per se. Or you might have seismic data. We'll discuss more maybe last quarter of the lecture. Again, you don't see the rocks, you see some geometries. So you have to make sense of this kind of remote data. There are properties of the rocks that you're trying to understand, to make sense of these depositional systems to be able to predict. And because of that, I will bother you a lot with what we observe in the modern. Okay, like modern environments, we try to observe and make rules and extract models. So when someone will ask you what you think will be this wiggles here, which might be just showing you thicker sands versus this thinner sands, maybe to no sand in that area. And this will be here, this is in feet, it's 100 or 200 meters thick. That's kind of resolution you can see things. Okay. So you wouldn't know exactly, but you have to use one of these models that we will keep talking about. So here is an example of how you might correlate, or geologists will actually correlate and talk with you. They will say there's some fluvial maybe here, this will be some deltas, and then maybe this was a lacustrine deposit, so they will say, well, here are some lacustrine rocks. I mean, if you look at the thicknesses here, it's quite it's 1,000 meters of lacustrine, whatever it might be. Within that will be thinner beds that the data here wouldn't even get to answer what that might be. But I'm pointing here that all of these depositional systems will actually help us to get into the detail of these thicker units here. Okay. And you as an engineer reservoir in the future, you'll have to work probably at smaller scale than the whole basin. So again, the source to sink exercise you will have images like this in Google, and you'll make sense of these rivers, deltas, shelves as you look at the modern. What you'll not be asked is what we'll discuss about today, like alluvial fans, Aeolian, or again, lacustrine. So you will see a lot of this modern imagery and the processes again, but we build into deposition systems of things that you already know. The sediments were weathered and eroded, transported, and when they're transported by mostly water, fluid at the surface, you can upgrade or degrade the bed. And then during the transport, you also sort the sediment. So all of that will come handy when we discuss our depositional systems. So someone asked me, and I have to put this Aeolian, and Aeolian is the same thing. This is kind of a Latin kind of spelling coming, so they use this AE, which is pronounced as E, and some people in books you can still see that, written. So questions about the positional systems, kind of pinch why they're important. So Aeolian means wind. So on today's map, with the black here is where you have fields of the Aeolian sand dunes. So where would you say they're most of these areas? If someone will ask you where the Aeolian sand dunes are and why there? Any idea? Someone dare to say? I mean, here, they're the most. So what is here?
Sahara.
Yeah, so kind of desert. So how about here? What's with this area? Here it's a high Andes, and then they receive little moisture because it's a shadow effect of the moisture coming from the Pacific. The Andes are kind of blocking that. So behind the Andes, it's relatively dry. Okay, so dry, Sahara, desert, if you like, there to call that. There are more other such areas here. So we have this Aeolian environments with little rain. Okay. So it's little water that actually transport our sediment, so it's just left the wind to do that. And indeed, if you put the climate zone map here again for the global, for the modern global distribution of the climate zones, you see what they call arid. It's kind of overlapping quite well with the areas where we have this sand dunes. So what I'm showing you this because again, you might have to work on rocks that are older. Well, I mean, for sure, because it's, most of the reservoirs are into older rocks like Miocene, Cretaceous, Jurassic. And then the trick is this Aeolian area, you'll find wherever it was dry at that time. Okay. So here it's another way to look at it. And this is, again, global map to keep it on the same topic on where the precipitation happening. And what the map is showing is this precipitation evaporation kind of ratio or coefficient. So again, when it's dry or arid or hyper-arid, the ratio is between 0.03 to 0.2. Okay, so it's more evapotranspiration, that means there's more water going out of the system than it's raining in or through precipitation. Okay, so what is unique to this versus what we'll discuss about the water transported sediment is it's a very thick flow. See, it's the wind moving the sediment. So what is the top of the air, of the fluid that's moving the sediment? Kind of strange question. Is the top of the atmosphere, really? Okay. But this, so you should see this through analogy with the sediments in the river, is that you pick sediments from the substrate and put it up into suspension. Same thing happened here, but you can't get two coarse sediments, you usually get silts or even finer sediments, but you put it up into the fluid, which is air, as high as you have shear stress within air. And you see here, for example, a sandstorm somewhere in Arizona. I mean, the sediments are picked up for tens to hundreds of meters up. Okay? So that will be the thickness of the, if you want, the suspended sediments within the flow. And because of that, the distances can be very long. You know, if you pick up some of this dust that will be silt and finer particles up to tens of meters up or 100 meters, and you transport it for long distances. Let's see if this YouTube is working. How do we do this? It's not a direct link. Let's see if we can just do it all the way. Just visually, so maybe many of you saw events like that, but just visually get an idea how dramatic such a sandstorm might be and what's happening with this sediment. Okay, so that is moving. It's like a turbulent flow within air, which peaked sediments because of all of this shear stress that we discussed about water transfer, but now it's in the air. And it's picking up and it's going as high as it can. There's no upper limit. I emphasize there's no upper limit because in the river, when the sediments are peaked, they can go only up to the top of the water. Okay, well, eventually the video is showing the dust cloud, the flow is coming over whoever is filming there. It's getting a bit dark. Okay. You have the link, you can watch it more. Because the next slide, I would like to emphasize how far these things go. You know, on the slide we say, well, you pick up this silts and maybe clay particles, and they go far distances. But how far? Here it's a figure from a study that has Africa to the right, and then here it's extent within the Atlantic, and you have the scale on the bottom in 1,000 kilometers. And what the study did, they went and sampled for wind-blown dust here, how much they found into the Atlantic. And they mapped that with distance, and they come up with that you have tens of centimeters here per thousands of year. Okay, so it's kind of slow rate. But this wind-blown dust is going all the way 5,000 kilometers into the Atlantic. How happening that? It's again, you have storms onto the Sahara, onto Northern Africa, and then all of that cloud that you saw before, the Aeolian transport of the silts, they go all the way over the Atlantic. And I put Miami 6,500 kilometers because sometimes you get that dust even on the other side of the Atlantic. And I mean, you don't look at that, but sometimes it was in kind of in the news that they got some red dust all the way onto the Florida side. And let's see if we have time. I will show you this because this is part of your Source to Sink, this Null School Earth website that you'll have to, let's see, if you open that again. Oh, I like Google more. Doesn't matter. So is that Null Earth website where you can you have also to use for your exercise. So in there, on this one, we'll zoom into this thing about Aeolian transport of Africa, and here you will be sent to look at the waves and currents for your source to sink exercise, how that disperses the sediments into the basin. But here we can look at the winds at the surface, and then you can choose different properties. So one of them is particulate. So what is within the air, the particles. And then you have to pick like 0.1, this is 1 micron, 2.5, 10 microns. Okay? You already see that what I want to show you is that hotter it is, more particles of 10 microns up into the air. Okay? We can get 2.5. So you see the pattern of the wind-blown particles over the Atlantic. And you can play yourself with this, picking a different date here. See, well, we can do that. And wherever you'll see when it's a storm, 2023, August, I'm not sure. I'm just, wait, wasn't too much storming. But again, when it was in the news that, hey, we get a lot of dust all the way to the Florida, I went and checked here, and indeed was a stronger transport all across for whatever, the winds were doing, the atmosphere circulation at that time. You can use this also to follow pollution, for example. If you want to see summer-winter differences within the Northern Hemisphere, North America or Asia, you can use this, but you have to pick some other particulate here, like sulfur or other things. We're not into that, but at least this Aeolian transport you can see clearly here associated with the North Africa, with the Sahara Desert. So the winds are usually are blowing here east to west, and they take some of this Aeolian dust all the way across over the Atlantic. Okay, let's go back to this. So we get now, this was just kind of transport and Aeolian, and where we find the systems and how it might affect large areas. But, how about the rocks? And the key point that's making this Aeolian deposits different than, let's say, the water environments is that the density is lower and the viscosity is lower. So what that means for our sediment transport, we'll be able to transport larger grain size or smaller grain size? Smaller, yeah. Okay. Because remember when we discussed about transport was something with the viscosity linked to it. So more viscous the fluid is, the drag force is higher, so it's easier to pick up larger sediment. So air transport another range of particles. Okay, so maybe some of the sand grains can also be transported, but closer to the ground. But most of it is very fine sand or silt or porcelain. Okay. And something else that I will show you on is the collision between moving sand grains, not viscously done. So when two grains come closer to each other in any fluid, it's the fluid in between that's kind of stopping them when it's coming closer. If that fluid is more viscous, then the collision kind of slows down faster. Okay? Because the air is less viscous, that doesn't quite happen as well as in the water, let's say. And that's something to emphasize when sediment is transported by air. And here it's how a diagram may show that. So you have some particles up into the wind and it's coming down at an angle and hit the substrate. When that is happening, it's what they call ballistic impact. So it's hitting all of the other grains that are on the ground there. And when that's happening, some of them are hit on a trajectory to go up, some of them kind of closer, push to jump around. And that's one way that the sediment's really moving down the flow, okay, through this impact. And what's happening through this saltation trajectory is, again, you impact some of this, and the grains are jumping, but similar to the water environment when we show, if there's some larger grains here, those, when you hit the ground, they kind of stick behind the previous, I mean, the grains are already previously there. And then we call that the creep surface movement. When you have this impact, one is jumping, it's hitting slightly the one on the ground, and this is kind of hiding behind. And here what's saying that it's a lot of grains are hit by this creep, the slow movement when the grains are hitting the ground, they keep moving the other ones, and that's what might happen. So why is that important is for us to recognize some of these sedimentary structures or the bed forms in Aeolian. And people that study this, they look at the ripples, the common bed form that we discussed into the aquatic environments, and the water is flowing over it from ripples first. Same, you have ripples made by the wind within the Aeolian environments. And the Aeolian ripples are straight crested to sinuous. Okay, I have some photos here. And what people notice that you have these fork junctures, so they will be kind of straight crested, but then they kind of come together like forming this patterns of forking. And the wavelength, it's the ratio of the length to the height. Again, this is crest to crest, the wavelength to the height of the ripples is between 15 and 70. So this is higher than the aquatic, let's say, ripples. And as you increase the spacing and the height, that it's increasing with the grain size. Okay, so coarser the sand is, or the silt there, larger these ripples are. So we'll have a higher ratio there. Again, these ripples, they form through this kind of saltation and creep, and they're not very thick here in terms of the forming the foreset that you saw before. And then you have this coarser material, which is kind of the one formed through creep and this impact migrating and sheltering some finer in between. So it's coarse to fine with some relief there on the floor. So that's what is making this ripples. And when you see them onto the rock, like preserved, they even get the name, they're called translatent ripple stratification. So this will be those kind of ripples. They're not very well defined foresets, and they're relatively thin, and then not so well preserved in terms of those, foresets of lee sites that we had for the test, for example. They show nothing of that. It's just an alternation of coarser and finer material. But nevertheless, if you look at when the bed form was active on the surface, it will be something like this, coarser grains and some finer grains alternating. And when this migrate, eventually is giving us this pattern of ripples. Okay. So notice these are not very thick. You have some scale here, a pen there, and then set a dime. So they will be just centimeters or thinner than that. So if you keep building some of this dunes, larger bed forms into the Aeolian, the smaller here, the orders, they start counting from larger to finer. We start from the bottom. So the height of the ripples, again, can get, they're from millimeters to centimeters, and they're we'll call again impact ripples. They will be the smallest, those kind of low relief ripples. When their transport is increasing, the higher velocity of the flow, you might get into what they call aerodynamic ripples. So this will be the one closer to normal transport, the one that you saw in Aeolian, where you have ripples with well-defined forceps. When you keep increasing the sediment transport, again increase the wind, you form dunes, Aeolian dunes now. And the dunes themselves, they form larger dune fields. They're called draws. And you have here with each of this different name of the bed form, let's say, with the structures, increase with the size. And something to emphasize here is that Aeolian dunes, they can get up to 100 meters. And you already have in mind images of that. You know, if you're in the desert, like Sahara or others, the dunes that you see, they're quite large. Okay? That doesn't happen onto the, let's say, water transport. And the dunes themselves, they have different names according to the morphology they get. So we go over some of these names. So the Barkhan, they form this horseshoe shape with the opening down the wind. And then you have something that's called transverse, where the crests are perpendicular to the wind direction. Then something that resemble the Barkhan, they call it Barkhanite, and again, they're not so well, I mean, where they're horseshoe shaped, but they're kind of touch each other, so it's more sinuous crest, if you want to call it like that. Another one is like what they call linear dunes. So the crest of the dunes tend to go down the wind direction, and this is formed when the wind is changing the direction. Let's say with the seasons. In 1 year, you know, in the spring, you have one direction dominating, or the summer, the fall, winter, you might change that direction. So the sediment is transported during both directions, but with different seasons, and the ending shape of the dune field will be what they call linear. The parabolic, its shape of the dunes is similar to the Barkhan in terms of the horseshoe geometry, but they're opposite to the Barkhan. So in other words, the opening is up the wind. Those geometries form when you have a substrate that is resistant to the sediment transport. So here they show some vegetation or some water table that's higher up. And the most complex, you have star geometries of the dunes when the wind is changing in the multiple directions. So it's a modification of this linear form. And if you have the wind changing direction often, let's say during the year, again with seasons, then you end up with something that resembles star geometries. So why these Barkhanoid geometries is this happen when you don't have enough sediments that is blown by the wind. So when you don't have enough sediments, or it's restricted the budget, you form this Barkhanoid. And here there are some examples of this geometries. So here it's an example of the linear dune. So it's not quite straight, but this crest, that kind of linear changing a bit, suggests that the wind is blowing from two different directions. What was on one of the graphs is that between the dunes, between the interdunes, what is called there, you might have water, and then you wonder why is that? Is because the substrate that's impermeable is close to the surface, okay? And the dunes are actually migrating or build on the top of that surface. And when you get rain, eventually the water is accumulating into the interdune area. And that's restricted some of the sediment transport. So there are other important observation onto the Aeolian sedimentary structures that's making us to recognize these were formed by the dunes. So if you go somewhere in, let's say, in Utah, area there, I mean, Arizona, you'll see large bed forms like that. We have a person for scale. So how do we know these are Aeolian deposits, we wonder? Because that's what they are. I mean, we're talking about that. So one thing is they're really large cross strata. You know, we discussed that this can get really large, meters, tens of meters at times. But then it's something else that's happening. I show a photo like this when we, you know, the very beginning of the class. So what's happening here, we look at the crest with the wind coming toward us. So we look straight at the dune here with the crest there. And what's happening, the sediment is coming on the Stoss side to the crest. It's deposited here. The coarser grain will just kind of roll and be transported right at the dune there. And they oversteepen like this. And when it's getting too steep, the gradient, they kind of flow on the lee side. So we call that grain flow. Okay? But some of the finer grains, they go over, and then remember they kind of fall in front of it. And that's a grain fall. So that's why on this graph or GIF that's keep repeating the animation, it's showing all of this darker color will be the sediments that kind of flow, and the lighter color is the one that come over and kind of fall in front of that one. And this kind of dual grain size is typical for the Aeolian, let's say dunes or cross strata. And here it's showing on the photo, you will look at the crest, you see some of this kind of darker conduits. This is where the sediments have a failure at the crest and form one of this flow. And here again more examples of that. So it's a photo taken when the wind was probably quite strong, and you can see it's fuzzy because it's a sediment closer to the substrate there, and it's transported across one of these crests of the dunes. Okay, and what's happening here with GA is grain fall and GF is grain flow. So the flow is forming all of these conduits on the forceps, like you have it here. Okay? And the fall is the one, the finer grains making us kind of image fuzzy here, but is coming over the crest fall. And there are again examples here of these forceps. If you look closer, you might see a grain size variability there. And a really close-up look is showing you here the grain flow, and this will be coarser grains if you look closer at the microscope, and this will be the fall at the laminae in front of this forceps. This is typical for Aeolian again. So to summarize, I mean, these bed forms, here it's a sketch with dunes. Okay? Well, you'll see, I mean, you already saw we have this under the water as well. They're dunes, and they migrate. When they migrate, they preserve just the forceps. Okay? So nothing tricky in that. You have the dune, you have the trough. But if these are in the Aeolian environment, what you have this separation of the grains on the forceps here, okay, with the grain flow forming these conduits, and the grain fall that will be finer in between and at the bottom. And if the crests are sinuous or the dunes, you actually might form ripples on these more prominent areas. And the ripples will have kind of strange angles to the whole dune. So this is kind of summarizing the characteristic of some of this cross strata of the Aeolian environment. Questions about the Aeolian before we go into the alluvial funds? I know it's a lot. Like I said, there are books written on that.
But the thing is, for you to know, there are different ways that we can recognize these rocks. The alluvial and fluvial fans, now we get closer to the mountains, and this will be, water transported sediments and the environment. So there are different words that people use for this. So there are alluvial fans, fluvial fans, fans altas. Okay. The fluvial, the word you mean, is coming from Latin and means river. Alluvial is again coming from Latin, it's to wash against, or something like that. Okay, so it's kind of river that's washing. But you notice that we use fan word for all of these things. So really describing a fan geometry of your sedimentary deposits. So we'll go over alluvial fans here. I mean, this is the emphasis here, but just to know the difference between different words. So alluvial fan, again, it's a fan geometry that is coming, we'll see in more detail, the sediments coming on the conduit, which is ended abruptly, and the sediments is kind of fanning out, forming the fan geometry. Now, some people use the word fluvial fans when actually you have a more permanent stream, like a river, a fluvial system. But that's migrating through time. And you end up with a fan geometry. But it's not ephemeral flows like in alluvial fans, it's more permanent. And this is migrating. This is Kosi fan in India. Our scale here is quite large. This is 20 or 30 kilometers, so it's 100 kilometers. Now, when you have this fan geometry, you say an alluvial fan coming into a basin, you use that as a fan delta. We'll discuss that. The deltas, they build into standing bodies of water. So if you have an alluvial fan that's ending into a basin filled with water, you call that the fan delta. But again, we'll discuss more about the alluvial fans. So where does this alluvial fan form? In high relief areas with steep gradients. And examples I showed you earlier, I didn't say where it is, but wherever you think you have high relief mountains, I'm sure you saw these alluvial fans. See, like fanning geometries coming out of mountains, high relief. Well, those areas have large supply of sediments, which was created through physical chemical weathering. All of the sediments that is coming off the rocks, different type of rocks the mountains are made, are weathered and then transported through some conduits, and then they kind of come and form fans when they come out of these high relief areas. And then they can be forming to the dry or wet climate, and they have high energetic water flows. Can be just one season that it's monsoon season, let's say rainy season, and that's when most of the sediment transport happens. But when it's happening, the sediment transport is high. And in many cases, some of this bounding of the upper part of the fans is bounded of some structures. And here we emphasize like a fault. What the fault is controlling is a high relief that it's coming from whatever canyon or conduit up the mountains into the basin. I mean, it's not necessary to have a fault, but in many cases, people describe this fault or some structure that's controlling the edge of this fans. Again, the alluvial fans, they form where they're a constricted conduit, like a channel that you see here on the top right image, that's coming it up into the open and forming this fanning geometry. So key to the alluvial fan is the flows is distributed over a significant fraction of the surface. So when the water is flowing over, it's fully channelized. Sometimes forming like what people say sheet flow, so the water is kind of expanding over it. And something else I will emphasize here, the alluvial fans are not very large in dimensions. So here this is from Death Valley, they say this is a road for scale. So this will be kilometers, 1 or 2 kilometers. And that's a typical size. While the fluvial fans, like I said, they're kind of more permanent streams that migrate through time. This is the same figure like you saw earlier, but now they're colored the location of the stream on the top of this fluvial fan at different times in the past, starting from 1700 from old maps. Okay? So this different type of sediment transport between the alluvial and fluvial fans. And again, I emphasize that the alluvial fans are not very large, okay? Kilometers, tens of kilometers. Why is that? Because then you lose this steepness. You know, the gradient is getting smaller here. You lose the sediments, the deposition here. So that's where your fan is ending. So what's controlling the flow over? And here there are some equations. You don't have to I will explain them. I mean, you'll remember them. You don't have to remember exactly. But here it's a slope. See what's controlling the gradient, the steepness of the fans. The channel width. There are flows on the top of these fans, but what's controlling how wide they are. Because I say on the top of the fans, the channels can get pretty wide. Like a sheet flow. So what's controlling that? And the channel depth. You know, if you have the flow over the fan, the channels never get too deep, but they're rather wide. So why we have that? If we look at this to say the gradient is a function of sediment versus the water flux. Sediment flux versus water flux. If you have a lot of sediment, what's happening to the gradient? It's getting higher or lower? Higher, so steep slopes. Okay? If you have more sediment, the channel is getting wider. So you just kind of grade the bottom, channel get wider. Now, if you have more water, what's happening with the channel? It's getting deeper. In the alluvial fan, what we emphasize, it's a lot of sediment because it's a high sediment supply coming off the mountains. So if you have high sediment, then you have high slopes, wide channels, and not so deep because again sediments will be higher here, so it will be a relatively shallow channel. And because of that, the flow when they come over, they get wider. And here it's I mean, just to point to some ratios for a single channel versus multiple channels, and the ratio of this channel width versus the channel depth. So when the ratio is high, then you have one single thread. When the ratio, it's the other way. When the ratio is higher, then you have multiple channels that eventually turn into like a sheet flow, a really wide, maybe multiple channels. So, so it's something else also with this coming out of the constriction. So if the flow is constricted within a canyon there where a conduit, when it's coming out, it has to expand. And that's where you start depositing the sediment. When the flow is expanding, the velocity decreasing. Remember that? When we talk about the transport, decrease the velocity, the average velocity, you decrease the shear stress and you start depositing sediments right out there. But a lot of sediments. And then the flow is getting over, having still a lot of sediments in the flow is no, let's say, confined flow or well channelized, and it's kind of fanning out, giving us this geometry. And here the photo, it's interesting, it's showing actually a fault. So right at the apex of this fan here, it's a fault that's kind of controlling probably the conduit rather than the fan, or indirectly the fan location, or the apex of the fan. Again, these are in the Death Valley. So why in the Death Valley? This is, I think, second, third images showing. Why do we have this fans in the Death Valley? Why not here? just say, what do we need for these funds?
Elevation change.
The high relief, okay, and more sediment, so high relief, high weathering, or maybe the seasonal flows like flash floods, so the water will be able to have high suspended sediment material, really weathered, ready to be transported, forming the funds. Okay, so the relief, weathering, and maybe this high precipitation events. So it looks complicated, but it's not. You have the fan geometries, but then we emphasize this kind of sheet flow unchannelized, but some of the fans they do have more channels. So people classify then alluvial fans in two types. One is debris flow dominated, and one is stream flow dominated. So in other words, some of them they're more channelized and form like watery flows, and some of them they have so much sediment within the flow that they will form something we call debris flows. And we briefly mentioned that when we talk about sediment transport, and we say, well, within the flow you can increase the sediment so much that it's increasing the viscosity, and you have water sediment mix highly viscous, and we call that debris flow. So some of those flows are building the fans. I'm getting closer here. So again, just to know, the geometry will be maybe similar, but the stream flows, according to this model there will be more kind of channel, like conduits drawn here. The debris flow, I will show you some images. I mean, they really have this kind of smaller, lobate, elongated geometries to it. And you wonder, why should we know about this? Again, remember, different type of flows will have different deposits, and because of that, different properties of the rocks. You get to that all the time. It should be on your mind. So here it's an example of water laying gravels and conglomerate flows, maybe coarse sand. So it's still a stream. So you have water through the channels, and it's transporting sediment, sand, gravel, and you saw that. Then you end up with stratified deposits within the bars. There will be the areas between the channels. If they cluster large enough, you'll see them imbricated. You remember about that when we discussed structures that point to the flow direction. And so this will be more kind of water-driven flows. But let's look at maybe debris flow. That's something new to you. Again, we'll look at some videos that you got the idea in mind what's happening with the sediments, and then we can look at some deposits. But let's see some debris flow in action
today
here.
about debris flows.
And this is from China, Yunnan province.
Debris flow is a highly viscous flow that has the capability
water
of causing massive
is
destruction
flowing
and death.
and it's picking sediment. Let's say
Debris flows are 100,000 times more viscous than water.
There are four conditions necessary.
these guys explain better than me, so turn them off. So you have again. So you have the water picking up, let's say, clay and sand, and that mixture is increasing the viscosity. So what's happening when we are more viscous fluid? You can pick even larger grains and larger. Okay, so that's why you see some boulders there moving through. Okay, I mean, you can watch this if you like. Let's look at this one. This is also quite dramatic. This is somewhere in Switzerland. Oh, advertising. So why Switzerland again? Why these debris flows are common in Switzerland?
High relief.
High relief, and they have water melts there, or maybe some flood events, but they have a lot of water melt flow. I put the things to remind me. It's a long movie, but the most interesting is coming from 30 seconds up. Okay, so you have one of these valley where this I discovered by looking some of the videos like that. It's famous, so you know when there's big rain, people go watch this debris flows. So it's coming down of some valleys like this, and I think they're on a bridge filming it. So the thing is this, any transport we're talking, think about this, you just start with the water, picking up sediments, getting, filled with sand and mud, then it's increasing the viscosity, and because of that, it's keep picking larger and larger boulders. And the flow itself is getting heavier, so that density driven is keep moving boulders down the flow. The debris flow. Okay. You don't want to have anything in front of, in the path of these flows, okay? Nothing. And they're tricky. The way to stop these things, ESGS had some experiments. We have time for a small chit chat. So how do you think they stop these things? I think in Switzerland they do the same. Onto the path of these things, and ESGS has experiments to that. They put they put like a, not concrete or metallic things with holes in it. And when the flow is coming over, it's high pressure within the flow itself, as you imagine, to move these things. But if the bottom is porous, it's losing the water. And then it stops. Because they increase the friction within the flow and it stops. ES just has some experiments with that. The debris flow coming, and they have one of this kind of hole through kind of area, and the debris flow stops. I don't know what to call that, the debris flow preventer, or anyway. Okay, so here it's a lot of text on this slide, but the point is that debris flow is moving because it's elastic collision. So you have grains within the flow, they bump into each other and they keep moving it and they kind of vibrate. I'm not sure if it's the right word there, but they just move into by each other and then inertially bump into each other. And here you have to keep in mind it's a mixture of fine-grained sediment suspended in the water. Okay, that's how it starts with, and then can get larger and larger grains. They can get up to boulders, like you said. And it's a viscosity that's increasing and allowed to get larger and larger grains. And here it's something I emphasize with the high pore pressure. So it's a high pore pressure within the flow itself, that is keeping the larger grains keep moving. And if you lose this high pore pressure, if the viscosity is getting too high, so the grains can move and bump into each other, then the flow stops. And here you have an example of kind of strange flow like you saw before, but then kind of frozen or stopped, and now it has some relief. The same images was shown on some of the videos from ESGS, if you want to look. When I say they put like a porous substrate and then they're losing the water and the flow kind of freezes. But it's interesting what you see when that's happening. So here was the flow coming, and look, it has this kind of edges on the side. You can still see them here. And that's where the sediment stopped moving first, because the edges was more friction and was probably also losing water on the side. So it was getting too viscous to move. But the flow was continuing through the center till eventually it also kind of lose the water. Increase the viscosity too much, kind of stop. So here it's emphasizing this kind of Levy geometry. Anyway, so strange things, but again, we have this fans, they're dominated by such flows, like you saw in the movie. So they come down the conduits here, they're constricted. When they come out onto the lower gradients, out of the constrictions, they flow kind of different direction, forming this, what we call the debris flow dominated fans. How we know that? Well, you go onto these fans and you see this mixture of particles from clays to sand to large class boulders within the same bed. And there's no other way to transport such a poorly mixed type of sediment. You know, the normal water wouldn't do that. It will sort sand from mud, from larger pebble class. So to remember, when you see rocks like this, see this is like a fist size scale there, top of the camera lens, and they mix with sand and mud within the same bed, you call that a debris flow deposit. Or they use the word dendrites, if you want to clarify that. Okay? So here you have somebody else pointing to some large class, but they're mixed with finer grains. So it's a debris flow that was depositing this type of bed. And then there are some other things. If you have a lot of mud within that flow, similar to what you saw, but sometimes large clasts mix with that, they call it a muddy debris flow. So it was dominated by mud, with a lot of mud into the mixture, but was still flowing like a plastic material. Okay, but first you recognize it's dendrite just because it's kind of mixed inside, but also there's some larger clast, outsized clast within the flow, and then you can move that within the muddy flow if it was not like a debris type flow. Okay. Here are the examples with a student from our school here looking at some debris flows in California. I wouldn't ask you again why California and why Southern California. You already get the idea. High relief, kind of dry area, flash floods. But these are Miocene rocks, so it's some million years old. And you have a scale here. This is like tens of meters, kind of thick. And the student looking at it, and here's a measure section, you know, describing bed by bed. The labels are pointing to some beds that they, you know, from the drawing you get the idea they have large clast mixed with what we call matrix, sand and mud. Okay. So this is pointing to clearly debris flow deposits or dendrites. In between, water lane, they will be better sorted and better kind of structured within the beds. Okay. So this, what we call alluvial fan deposits, they have elephant tree formation they call, but each of this bedding then, some of them will be debris flows, some of them will be more watery flows. So, a question, are these good for reservoirs? We come back to that all the time. I will buy you a question on that. You say no, why not? Oh, the porosity. And? Grain sorting, yeah. So poorly sorted deposits, they have low porosity, low permeability, as you remember. So if you have these beds, I mean, they wouldn't be good reservoir. But there are other things. The connectivity, you know, they're quite discontinuous cutting to each other. So laterally wouldn't make good connections. And something else you need for your reservoir, you need a seal. You need some impermeable rock over it, maybe even regionally, to kind of close your reservoir or seal it. Well, in this environment, so we're talking, you know, high up the mountains, alluvial fans, coarse grain, what the seal can be. I mean, what shell we can put on the top. It's quite difficult. So these are not good reservoirs. Not to say that there are exceptions, obviously. You know, there are other things that you can do to these things. But in general, they're not good reservoirs. We have just maybe 5-10 more minutes. We'll start into the lakes. So questions about alluvial fans? Simple. So we get into the lake systems. We'll see how much we can get into it. I probably will not finish. But the lake systems, what is good to remember is that it's defined as an inland body of water with no connection to the open sea. Austin Lake, it's a lake. It's just isolated body of water. Any body of water you know about on the surface of the earth, it's not connected to the ocean, call it a lake. what you should have in mind from our point of view is that highly variable, physically and chemically, because they're isolated from the ocean. Each lake will have its own properties in terms of salinity, biota, whatever is living in it. Any current or water circulation is different. So they can be shallow or deep. We'll show that. Can be fresh, brackish, salty, very salt, hypersaline. They can be long or short-lived. We have our lake here, it's just from the 60s, I think, the Ladybird. Okay, but some of the lakes that are right now, they're millions years old, have different shapes. So here it's a map, global map that shows the river drainages. So by the color is where the rivers are flowing into. So the green here, it's into the Atlantic. Let's say the purple, these rivers flow into the Pacific. But the dark gray or blackish, it's the rivers flow into closed basins. They don't go into the oceans, but they go into closed, what we call lacustrine basins. So you see large areas of the continent here, maybe Africa, North Africa, and part of Asia. The rivers are flowing into lakes or kind of interior of the continent. And notice it's quite a large area. Okay? So no ocean, the sediments are not going to the ocean, but they go into these lakes, accumulating sediments, and sometimes, organic rich rocks. Sometimes some of these lakes, they have the right conditions to form reservoirs. Again, this, no point to emphasize much, but they have also some link with maybe it's interesting, this climate control and things like that. So, how do we form a lake? What do we need for that? Well, we need a depression or a hole on the surface of the continents that will not be linked to the oceans. Okay? And then we need a positive water balance. So you need to have more precipitation than evaporation, so the water will accumulate. Otherwise, there are some depressions somewhere around Sahara where it's a bit dry, in some other parts, that they're actually empty. They're depressions, but there's not enough rain to fill it. And then, as you imagine, more precipitation, larger the lake or the basin is getting. So here you have a Lake Tahoe, for example. It's a depression. It's accumulating, I think, mostly during the winter snow water. Has a relatively small drainage area. So here it's an outline of the rivers or the streams that get into the lake. It's not very large, but it has precipitation higher than evaporation. It's enough over the years to actually collect the water there. Now, origin of the lakes. Where these lakes form, and the tectonic origin is the most important. Okay? So the question is, where do you have these depressions? How do you form it? Where? So it's tectonically formed depressions are the most important because you're the largest. So you have extensional, like rift valleys in East Africa, and Baikal Rift, strike slip, so with the plates moving, one passing by the other, then you kind of break the crust and they form depressions. Or we'll see in compressional settings where the continents, they come to collide. The area in between, maybe it was an ocean before, but it's becoming isolated and it's turning into a lake system. The Caspian Sea, it's one of these remnants. The Mediterranean is not quite close, but in past was close as a lake. The Black Sea, the same. And okay, well, let's see. Maybe you saw that before, but just the idea that. Okay, Squatisi. Let's see. We can move faster, closer to us here. So these are different geometries, but so the idea is. You form lakes here where you have a rifting of the South Atlantic. See, when the continents are breaking off, will you form depressions where eventually the water will accumulate from lakes. We call that rift lakes. East Africa, it's happening exactly that what happened to the South Atlantic right now. We have rift lakes there. And the other thing is, oh, this is not running or is running too slow. The other thing is, here was a Tethys Ocean, and when let's say the Africa and maybe Arabia collided with Asia, you close that basin. You go fast here doing that, and when you do that here, you end up with lacustrine basins. Like I say, Caspian, Black Sea, Mediterranean. These are remnants of the ocean and form lacustrine basins. And why these are important again is as they isolate from the ocean, they have different characteristics by themselves. Okay, so it's important to consider them different than the ocean settings. I think it's 15. We stop here. We continue next with different type of lakes and rivers next time.